An algebraic generalization. There is a section of algebra taken in school in some countries and in the first year university work in others, which serves as an excellent illustration of the generalization. This section might be thought quite unsuitable for a treatment in a popular work. First, it is at or near university level. Second, it involves or can involve very long algebraic expressions. Third, students do not find it particularly easy. Nevertheless, I intend to deal with it now. The above objections are met by the following considerations. First, only an elementary knowledge of the algebra is needed and no long calculations occur. Second, although the expressions are long, they have a very definite pattern which the mind can grasp. Third, the whole thing grows from a single idea which is usually not mentioned in the textbooks. The single idea is the following. Try to generalize the fact that there is a one and only one straight line joining 2 points. Now, of course, this is, as it stands, a geometrical result and we might begin looking for a geometrical generalization. Someone may suggest that the fact that a circle can be put through any 3 points. Someone with a little wider knowledge may know that a parabola can be put through 4 points and a conic section through 5. But there we run into something of the dead end. Nothing springs to mind as going through 6 points. Accordingly, we do what we did in chapter 3. We tried translating into algebra. That is easy enough. It is well known that any straight line except a vertical one can be got by choosing the constants m and c suitably in the y. In y equal mx plus c. Right. Y equal mx plus c. A point is specified by a pair of numbers. Our geometrical result when translated becomes: it is always possible to choose m and c so that y equal mx plus c passes through 2 given points a p and b q. Right. We should add that a and b must be equal, for then would lie on the same vertical line and the gradient m would have to be infinite. Right. Instead of saying that the line passes through the points, we could write the equations. P equal ma plus c 1, q equal mv plus c 2. 1. These state that the expression mx plus c takes the value p when x equal a and the value q when x equal v. Already an algebraic aspect of the problem has appeared. We have 2 quantities m and c at our disposal, and 3 are 2 equations that they have to satisfy. But we are quite used to solving 2 equations for 2 unknowns, right? Yes. We expect given 2 equations for 2 unknowns to be able to solve them. This suggests that if we want to put a curve through 3 points, we ought to find an equation with 3 unknowns. For example, y equal gx squared plus hx plus k, where g, h, q are at our disposal. Now, this idea is in fact correct, but we have not yet proved it. Unfortunately, it is possible to have 3 equations in 3 unknowns with no solution. Consider, for instance, the equations g minus h equal 1, h minus k equal 2, k minus g equal 3. These have no solutions. The first tell us that g is bigger than h. The second that h is bigger than k. The third that k is bigger than g. It is impossible to find 3 numbers for which this is true. Actually, exceptional equations of this this type do not arise from our particular problem. At any rate, they do not arise if we try to find y equals gx squared plus hx plus k to pass through 3 points, bracket, open parenthesis, a, p, open parenthesis, b, q, open parenthesis, c, r, where a, b, c are all different. This can be shown by means of the determinants which are discussed in the chapter 9, right? They would arise if say A equals B. Suppose we tried, for example, to find a formula of the type just considered to fit the table x 113, y 245. This would mean that when we substituted x equals 1 in the expression gx squared plus hx plus c, we should have to get the value 2 and also the value 4. And of course, the same expression cannot have two different values for x equals 1. This argument incidentally shows that there must be exceptional system of the equation which have no solutions, such equation must arise wherever we make ridiculous, self-contradictory demands, right? They are mathematics' way of saying no. They are mathematics' way of saying no. Fortunately for the scientific workers who often have to fit curves to points given by experimental results, the insoluble equations occur only when we ask for something obviously ridiculous. In this problem, there are no unreasonable catches. If we take any 3 points corresponding to a different value of x, we can in fact put a quadratic graph through them, and it goes on in this way. To 4 points we can fit a cubic, to 5 function of the 4th degree, and so on indefinitely. But this is still unproved, unless we are going to use the theory of the determinants, to which we have not yet come. Quite apart from the proving that there is a function, it would be good to know what it is. If we can actually find the functions that solve the type of problem we are considering, this will automatically overcome the difficulty of proving that such functions exist. It will also save us solving equations every time we need such a function to fit experimental data.